Hi folks, gonna start up pretty soon. Hopefully there are a few people joining me today. It's always great to have a nice live audience. Glass of water for my lecture and then I'll come back and we can get started. Probably a good idea to have my slides served locally. Ooh, someone's got a really interesting question on Piazza. I wonder if we'll be able to answer that in this lecture. Probably not, but just because the more interesting the question is, the more effort it would, I don't want to do that, the more I would have to think about the answer. Oh, I got a good audience today. Thanks folks for joining in. Always a pleasure to have a team of you watching. Okie dokie. Just make sure I've got everything ready. I do like to have everything ready before I start. Good morning, folks. Great to be here with you. Here on a Monday afternoon. We're back on the regular Monday time slot. No more public holidays this semester, so we're in the home stretch now. The second half of the course has really begun. We're now doing the part of the course I like to call the tour of the topics, because we have a slightly different topic to look at each week, which is going to be adding to your understanding of how a computer works, adding to your understanding of what you can do with your microbit, and building on everything you've done so far in COMP2300. So we're looking at different topics, touching on a lot of the things which tend to come up as questions in the first half of the course. Oh, how does this work? How does that work? People asking me things during lectures, and I say, just wait until the lecture where we spend a significant amount of time talking about how that thing works. Well, here we are. We're ready to spend a significant amount of time on how a thing works. And whoops, where's my little scribble pad? The thing that we're talking about how it works today is this idea of networks, but I also suppose, just to add a word here, networks and connections. So the broad question is, if you've got one microbit, this one's number 1, and you've got another microbit, that's more like a 2, isn't it? A 1 with a thing at the bottom, and you've got a second microbit, number 2, how can you get data from number 1 to number 2, and how can you get data from number 2 to number 1? How can things go both ways? So at the lowest level, this is about small connections, small electrical connections between multiple computers. At a higher level, it's the fundamentals of how computers connect together, how they send messages to each other, and that gives us really important networking technologies and big things like the internet, right? All the computers talking together in interconnected networks, and they have common ways of communicating data, agreed over many years. So I know that it's a, there's already a good question in the chat. I know that it's an exciting topic to think about networks. To some extent, I want to say to you, we're going to treat this like everything else in COMP2300, which is to start from the ground up. What do we need to do this? And we'll learn about some of the complexity that we come into when we try to connect computers to other computers. And we'll use that knowledge to help motivate some information about how things really are in the world of networks. And of course, this is just 1 week of discussion. We'll do some things today which are really unique. You probably won't see these in any other course. And then there will be a lot of things in this course which open up questions to be answered by later study in networks, if you go and take our networking course, for example. So we're not covering everything to do with networks. It's not a substitute for the networks course, but it's certainly a start, and it's something which will give you experiences today and this week and next week in your lab that you won't get in other courses. The network week. What are our topics this week? We talk about the basic fundamental language of networks. What are we talking about when we're talking about connections between computers? We'll talk a bit about a serial connection and a particular type of serial protocol called Midi. And we'll talk about a sort of big, highfalutin, complicated way of abstracting information about networks, and we'll understand why that's important, called the OSI model. And then we'll just tour through a couple of other important standard protocols related to how networks work. Admin time. I'm going to answer someone's question. The question is, when are you expecting to get your feedback and your mark from the mid-sem exam? I'm aiming for Monday next week. I think we have a protocol in this course that we do a 14-day turnaround for feedback. Or a 2-week turnaround. I guess I should clarify it and say it's 10 working days, because the amount of public holidays has really messed things up for us this semester. But you did a mid-semester exam. I know that was a big challenge for everyone. I'm sure you're concerned about getting your feedback back for that, but we do need to have a good chance to mark it thoroughly and figure out how to get that back to you. So I'm going to do something for my health, which is not make promises I can't meet, and say I will get you that feedback on Monday. Let's see if I meet my promise. There's nothing particularly urgent for you to do with that feedback except, study for the final exam. So it's I don't think there's a pressing need to get it back today or something. You'll get it back when it's ready, within a good period of time. Little wires. What are little wires? These little things is what I'm talking about. These little nippy nip 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 nips. See? Little clippy clips. Sorry, I can't speak right now. Crocodile clips, alligator clips. They've got a little jaws. They look a little bit scary. What am I talking about these for? Well, in your lab next week, you're going to be doing networky, connection-y type stuff, connecting microbits to each other with extra electrical connections that you'll create yourself. You might have noticed at the bottom of your microbit that there are these little gold-colored areas. Those are connected to, or mostly connected to GPIO pins on the CPU. And handily, if you've got one of these little clippy wires, you can clip to one of those, the big areas that have got a ring, and connect your microbit to your friend's microbit or even to itself. So if you're playing along at home or you're remote, you can get yourself some little wires. I've got instructions on the website. I just put out a message on the Piazza over the weekend with updated instructions. But if you're not in Canberra and you want little wires, go order some right now so you'll have them ready for next week. If you don't want to get little wires, well, you can find some way to make an electrical connection between pin ring 0 and ring 1 or ring 2 yourself, either with like paper clips or something, or a bit of wire. Just strip off some of the insulator, the plastic stuff, and wrap the copper wire around the little hole, and you can make an electrical connection that way. But for everyone who is in Canberra, we will have tons of these little clippy crocodile clips available in your lab for you to try out and have some fun with in Lab 10. What else? Assignment 2 pre-submission. This week is an assignment pre-submission week. First thing, before your lab, make sure you have forked and cloned the assignment template, assignment 2 template. Make sure you have filled in your design proposal. You have committed it. You have pushed it back to GitLab. You've gone to the GitLab website and looked at the file and seen your words and said to yourself, wow, I've really pushed it because I can see it on the website. So make sure you do those things, because that way, when it gets to your pre-submission lab and your tutor says, let's talk about your design proposal, they'll have it within their file and they'll be ready to discuss it with you. So remember, the point of the assignment 2 pre-submission is for you to read the assignment, to have an idea, to make a decision about a way you could do the assignment, write it down, and then discuss with your tutor about whether that's really what you want to do. So it's a chance to have a go at your first cut of just the assignment idea without, in a low stress environment before the assignment deadline is looming. Okay, that's all the admin time for this week. Let's get to the content, the basic concepts of networks. We're going to do, I think, about an hour of content talking about how networks work, how connections between computers might work, and having some fun in the chat. And then we're going to do what I think is the most ambitious demo that I've ever done in COMP2300, which is that we're going to try to send some serial messages with a microbit in bare metal assembly right here. It's going to be exciting, so keep your hat on for that one. Keep your socks on until then so I can knock those socks off with the excitement of this demo. That'll be a lot of fun. So stick around. Make sure you're here for the second half. Don't jump off. I think COMP2100 is right after me. So sorry, Bernardo. You just have to have low attendance this week because everyone's going to be in my demo. Or maybe it's at 4 o'clock. So I won't go past 4 o'clock. So Bernardo should be okay. Basic concepts. Here's the concept. We want to communicate with others. Someone's messaging me. We're sending messages to students' microbits. COMP2100 is not today. Sorry, I'm confusing people. We want to communicate with other computers. What's hard about this? So far, every time you write a program, every part of your program has the same registers that it can access and can access memory. So you've got some memory. One bit of your program writes to a location in memory, 0x2370s. Write some numbers there. Another bit of your program can read it. There's no way to prevent other bits of your software reading that shared data. Everything is shared. You've got global variables, you've got data sections, you've got function calls that are all shared. But so far you've only ever been working with one program on one computer. What if you've got one microbit and then another microbit and you want to get some information to the other one during a program? How are we going to do it? You know, don't all answer at once, but it takes a little bit of thought about this, right? Are you going to have some connections between these computers, or is it going to be some kind of wireless connection? If it is, how are we going to tell it what data we're sending, and when is that data going to be sent? It sort of comes back to this question of the big blank memory space, right? The big undifferentiated mass of memory. How do we know which bits of memory are the start of important data and which bits are not? And we've started to learn about in our data structures module how we might start to differentiate memory and put it into structures so that we can make sense of it later. And network connections between different computers requires some of those skills, but it gets a little bit trickier because we also have to handle the complexities of making physical connections between two computers and connecting data that way. So you've got a microbit, and you've got a wire connecting it to another microbit. So what is data going to look like? On my previous page, I had this thing, data requires difference, and we know about the difference between zeros and ones in memory. But what about on a wire? So what is the difference going to be on a wire? Someone, don't all answer at once, but someone tell me an answer volunteer an answer for me in Teams. How many different ways can we achieve the concept of difference in electrical signals? I'll wait. There's no one volunteering one right now. I guess the bunch of you watching on YouTube now are too shy for the moment. Oh, voltage. Someone says voltage. That's a very good option. So we've got a wire. Here come the options. Flow of electrons, voltage, energy of the electrons. Yeah, but what, I think one of those is the one we're going to be interested in, forward back. That's cool. The idea of forwardsness and backwardsness. I got my drawing here? Yeah, okay. So it tends to be, I guess the thing we can do with an electrical signal is change its voltage. So we can change the electrical potential. Between something we would call 0 volts and then some top end. And so electrical signals can have changing voltages, and you know from working with assignment 1 with GPIO that you can change the voltage on a GPIO pin from being low, which would be in this graph equivalent to 0 volts, to high, which in this graph would be next to 3.3 volts, because that's I've chosen 3.3 not for no reason, but because that's the power level that the microbit operates at. So you can make something be low and go high, or you can make it be high and then go low again. On your microbit, you can't exactly do all this stuff. That's a bit harder. That would require more circuitry. It's possible, but it's not something we have the capacity to do right now. So someone says, well, we could have the voltage could be the difference. So the difference in voltage. That one's 0, that one's 3.3. Therefore, between this area and this area, we have a difference. Is there any other way of representing information using a voltage on a wire? Oh, someone's got a cool idea. have AC signals and change its frequency amplitude. So I guess we could have a repeating signal. AC means alternating current, but we could have a repeating signal, and we can't change its amplitude with the microbit very easily because our amplitude is always 0 to 3.3 volts. But we could change its frequency, so we could be having these pulses here, and then we could have a section that's like this, really frequent. Oops, I'm out of space. I need to go over here. Oh, it's gone into that bad mode. I've lost my diagram. I have to start again. So here's the slow frequency, and then the high frequency, that bit. So if it detects high frequency, we could be calling that a 1, and if it's low frequency, we could be calling that a 0. Another way, you might have heard this term, pulse width modulation. So we might be able to have the same pulses, but the length of the pulse we might be able to change that. So you could have a short pulse, a medium pulse, or a long pulse. Another one I'll suggest to you is that you could always have up and downs happening at a certain time. But if the voltage is going up across that time, that's a 1. And if it's going down across that time, that's a 0. So an upward intersection is a 1, and a downward intersection is a 0. That's another way of doing this. So even though we've only got the capacity of moving a voltage up to the full voltage and down to 0 volts, we could have a number of different ways of expressing ones and zeros, different kinds of a difference between a Boolean number on that wire. So back to network connections. There's a few dimensions of networks that I want to talk about, and we'll talk about these today. One of these would be the medium of transmission. Another one would be the kind of protocol that you're using for communication. And another aspect would be the topology of a network. So generally a network would be between more than 2 devices or 2 actors on the network. You could have 3 things or 5 things, and there could be different ways for them to be connected. They could be all connected to each other like that, or interconnected. I mean, folks have probably done a neural networks course where you learn about fully connected networks and partly connected networks. There might be one in the middle which is talking to all the other ones. And so if they have to send a message, it's got to be routed between the middle guy. Anyway, that's topology. It's the shape of the network in terms of what the connections look like. So these 3 concepts, and we'll talk about a few more concepts shortly, these are all partly kind of orthogonal, or they're independent concepts. So when we talk about networks, well, you might be able to have multiple different transmission mediums and one topology that would work. You could have the same topology on those different transmission mediums. It's not like one transmission medium always has to have the same topology. So what do I mean by transmission mediums? Well, what's a node? I've got my slides in the wrong order. What's a node on a network? Well, it was one of these computers talking to each other with network connections between them. That's a node. Some sort of computer. It's not always like a laptop. Sometimes it's a big server, a whole room of computers. Maybe that's lots of nodes all together because they're talking to each other too. It might be a regular laptop or desktop that you have. It might be your phone. It might be an IoT device, not least of all a microbit, which is an IoT device, an Internet of Things device. I suppose in a science fiction world, it could be a nanobot that has a network connection and lives in your blood and makes you better or something. I don't know. We don't really have nanobots, do we? So that's a bit science fiction. What about transmission mediums? This is where I thought we were going. You can have lots of different ways of connecting computers. You can have electrical voltages on a wire or several wires together. you can have a kind of big wire called a coaxial cable, which if you take a cross section of it, this is a cross section through the cable, there's a core, which is one connector, and then there's another ring of conductor inside there. So there's the ring, or the shield, sometimes it's called shield, and that's the core. It's called coaxial cable because there's only one axis. That's the axis, and there's the two wires are around it. One's like in the middle and one's in a ring around that. You can have twisted pair cables. These are just different kinds of cables, by the way. Twisted pair cables have lots of little cables. They just have one conductor in them, but they're twisted up. So your regular old blue Ethernet cable for your computer network cable isn't twisted pair cables. It's got a bunch of pairs inside it, all twisted up. And many other cables have twisted pairs. I think HDMI cables have twisted pairs. I'm not sure. Someone can correct me on that one. EM waves in the air, EM standing for electromagnetic. So radio waves is what we really mean. We could be connecting microbits connecting to another microbit with its radio antenna using Bluetooth. It's the same kind of EM waves as Wi-Fi devices talking to each other. These are supposed to be Wi-Fi routers. It's also the same kind of radio waves as iPhones talking to cell phone towers, right? It's just different frequencies, different ways of organizing things, different power levels, different protocols, but it's the same transmission medium. Light in an optic fiber cable, so you've got your optic fiber cable. It's got a shield as well around that, a rubber kind of protector, and inside the cable the light's bouncing along the inside. Any other transmission mediums? Tell me a transmission medium. Oh, there was a really good idea for a way of representing zeros and ones. If a signal changes, it's a 1. If it stays the same, it's a 0. Cool idea. What's another transmission medium? Someone said to me, nice physics. I'm not sure if they're being sarcastic or not. Lucky I'm not a physics teacher. Yelling the binary across the room, that's like a sound-based. Great idea, by the way. Yelling. That's going to be a limited distance, sound-based yelling. But not a totally silly idea. Even for computers, there has been people who had this idea that, well, if you just need to get a little bit of data and you've got a speaker and a microphone, you could just go on the speaker and make some little sounds which the other computer could hear with its microphone. So totally possible to have a sound-based system. In fact, when I was a kid, everybody used sound-based systems for computers talking to each other because we had dial-up modems that ran over the telephone system. And, you know, it was an audible system. Usually you'd wire the thing straight in, so it wouldn't actually have a speaker. But there was an era when there would be these kind of modems which, this was before my time, but sometimes there was a modem where you would actually like put the telephone handpiece onto a special, like, this is a bad telephone handpiece, but that's the telephone, and you'd clunk it down on top of this kind of microphone and speaker, and it would just go have an auditory connection between the computer and the phone line and the other computer at the other end. Lights are EM waves in the air. That's right, indeed. So we've got EM waves in the air, and light in an optic fiber cable. The medium here is different. That's in air, light in the optic fiber cable. One of my favorite transmission mediums is in, if we go back to the lecture on functions, do you recall the COMP2300 generic adventure story? Well, in the second part of the subsequent 3 books of the COMP2300 generic adventure story, there was a town which had a big castle, and another town with people who rode horses. It was on a hill, and they had horses. And the horse people were waiting for the people in the castle town to say, we need your help. So they would have, the castle town had this sequence of bonfires on the top of mountains. And if ever the bonfires were lit on fire, the horse people would be called for help. And, you know, eventually the bonfires went on fire. 1, then this bonfire was watching. 2, 3, 4, 5. And someone says, the beacons are lit. The castle town is calling for aid, and the horsey people had to go and help them. So that's a pretty, unless you've got a really big bucket of water handy, that's kind of a 1-bit system, right? Because you can only send, once you've burned your logs, you don't have any more transmission medium, unless you have to then go down into the forest again, get more logs, and come back and build the bonfire again. So it's a very low end system. Oh, someone said, anything through a liquid. We have air and solid wire. Well, you've of course got compression waves through liquid. Sonar you could use. Yeah, someone's saying Lord of the Rings. I don't know what you're talking about with this Lord of the Rings nonsense, guys. This is clearly COMP2300 generic adventure story. COMP2300 generic adventure story. Which is, you know, CGAS. You know, it's coming in a new film coming soon, starring those guys. Viggo Mortensen's going to be in it as a kind of generic rugged adventure character. Thanks for playing. And so Charles out. End of this course. We talked enough about transmission mediums. You can invent something through water. I don't know what that would be. Someone had a good idea, but we'd need to hear more details about how that would work. Here's the physics refresher. Voltage. Voltage is this measurement of potential for transmitting current through a wire. And it's a relative measurement, so you have the difference of voltage between 2 points in a circuit. Now on your microbit, you can see there's a bit here that says GND. That stands for ground. So that's like the low reference point on your microbit. Then you've got another one that says 3 volts. That's the high reference point. So you can have any value is possible between those two. But in general, the hardware here only supports being like right at the top or right at the bottom. So switching a GPIO pin on brings the voltage of that pin to match 3.3 volts, and sending the GPIO pin low brings that voltage down to match ground. So sometimes the values matter. It could be that, as I was suggesting before, it could be that high is a 1 and low is a 0, or the opposite way around. And it could be that the transition is sometimes important. That could be a 1, or there was a suggestion in the chat, transition at all could be a 1, staying the same could be a 0, down could be a 1, 1, 1, 0, 1, 0, 0, 0. So there's lots of ways of interpreting. Have this diagram here of voltages changing. Depending on how you're doing it, there could be different interpretations of what binary code this could possibly represent. What binary code could it represent? So that's just an example. We'll look at a real example, a real version of this a little bit later in this lecture. Okay, back to interaction time. I'm glad folks have started to enter into the chat. I want you to enter into the chat because it's time for ReactNet version 1. Folks, send me a React, and I'm going to try to work out what it means. I haven't got any Reacts yet. No, not a React. No Reacts was found. I would love to have this on my screen, but on Linux, Teams is pretty cooked. So, someone sent me a React. It was a hat with a cowboy hat and a saxophone, and a laughing person. Okay, so great. Thanks, folks. Says there's an emo guy, or girl, or non-binary, or other. So I'm going to say that saxophone is now a 0. That's equal to 0, and a laughing, that's got a hand in front of his face. laughing is a 1. So someone send me a number with those two characters. Saxophone for 0 and a laughing person for a 1. Oh, I've got to send a message quick here. I'm waiting for my saxophone message. I've only got someone. Oh, okay. I've got a cowboy hat and a saxophone. Wait a minute. That's not it. Where's the laughing person? Oh, cool. I've got 1, 2, 3, 4, 5, 6, 7, 8 saxophones and a laughing face. Okay, that's going to be, obviously it's little endian, so it's 1, 2, 3, 4, 5, 6, 7, 8. That's 0, OX. Whoops, I need to get my 4, 5, 6, 7, 8. That's OX0, and then a 1, which is going to be OX1. So I'm going to presume that there were 7 zeros after that as well. Spike has just sent me 100, which is saxophone and 2 laughing faces. So that's a 1. And then someone's just sent me a laughing face. That's just OX0. 1 laughing face. So I guess my question now is, well, this is good so far. I can receive 0s and 1s, but I don't really know things I don't know. I don't know when your message starts. I don't know when it finishes. I don't know if it's little endian. I don't know if it's big endian. I don't know if I'm waiting for, if there was part 1 of 2. Like someone sent me 9 bits of information. That's a weird number. Am I waiting for more bits and they just haven't sent it yet? Or is that all I'm going to get? Or was one of those bits an error? Or was one of them a parity bit or something? So I'm not sure. You can see we're going to have trouble with ReactNet at this stage. Oh, now someone's got React and different lines. This is going to be really confusing now. So I've got a 101. I mean, we're not allowed to have, there's no room for lines in our network. It just smushes them out. We don't even know. 101, 0, 10. 101010. Well, that's just a 6-bit number, so that was easy. Okay, ReactNet version 1. We'll come back to ReactNet later after a few more concepts. Knock knock. What happens after knock knock? There's only one, if you're an English speaker, there's only one possible answer for knock knock. It's who's there. And the reason that we know that there's only one possible answer for knock knock is that we have an established understanding that every time someone says knock knock, the next person has to say who's there, because this is in a culturally important formula called the knock knock joke. Which has the standard form 0, line 1, knock knock, line 2, who's there, line 3, something, line 4 is something who, and then line 5 is the punchline. I can't even think of one knock knock joke. Someone tell me a good knock knock joke in the chat, please. Where's the knock knock joke? Come on, folks. You got to have knock knock jokes to hand, surely, wherever you're watching your lecture. Something who. So you've got a payload here, or an address there, and a payload is in the punchline. That's line 5. The point of the knock knock joke isn't that knock knock jokes are funny, because assuredly they are incredibly hilarious. But the point is that we have an understanding about how to interact if someone starts a knock-knock joke. And so it is with networks and communications between computers. We have this idea of a protocol which establishes some rules for interaction. So there could be the knock-knock joke protocol for computers, in that one microbit sends a message representing knock-knock to the other microbit, and microbit 2 sends a message back saying who's there. So at this point, microbit 1 knows something. They know that someone is listening and it's their turn to speak. Microbit 2 knows that someone is trying to send them a message and it's their turn to listen. So they have a lot of information already, even at this early part of the joke, which is very unfunny. Not funny, but important. The setup is important. And we'll learn this more later today as well. Communication protocols. These are a set of rules about what to say and how to understand responses. In the computing context, we could have rules like how big are the messages going to be. That would have been useful in the ReactNet protocol. Are we doing little endian first or big endian? Is there metadata? Are we expecting some metadata that's stored in a particular way? Both sides have to agree in a protocol. Something like, oh, here's a knock-knock joke. Knock-knock, who's there? Dwayne. Dwayne who? Dwayne the bathtub, I'm drowning. That's a pretty good one. Knock-knock, who's there? Doctor? Doctor Who? Yes, because they're Doctor Who. That's a bad knock-knock joke. Someone said they find the knock-knock part hilarious. It's two good knock-knock jokes. Part of the fun of knock-knock jokes is that they are simultaneously very funny and very unfunny. Sort of cringy humor that we tend to like. Okay, how are network protocols like social protocols? And we know that social protocols sometimes go wrong and they lead to embarrassment. If someone says knock knock and someone says yes, well, everyone's embarrassed in that situation. The knock knock joke teller and the knock knock joke receiver are both embarrassed by the failure of the knock knock joke to proceed. So there's certainly possibilities for badness in when social protocols and networking protocols go wrong. A few network facts, an idea about sending networks to other people, sending messages to other people. So far with ReactNet, everyone's sending messages to me. But we could be sending messages to many people. And I'll just point out two ways of accomplishing that. One is a way called circuit switching. So the concept of circuit switching is that you have a dedicated connection to every single other person you could talk to. And in order to talk to that person, you go on their connection. So if I'm talking to, tutor Ben, I've got a special computer I only use for talking to Ben. If I'm talking to tutor Ichen, I have another computer I send messages to Ichen. In some sense, I guess that's like DMs, right? If you have a direct message in Teams, you have just one person in each of those messages. So if you want to send a message to that person, you go to their DM. You can do this in a physical way as well. So in the olden days, there was this idea of phone lines where there would be an exchange in the middle of town, connecting all the phone lines together, and someone would physically connect your phone line to the person you wanted to call in a big switchboard with a physical wire. Not too dissimilar from an alligator clip, but maybe with a big plug instead. So there was this idea of physical connections between callers and receivers. What's the other option? Oh, there's the switchboard. There's all of these ladies working hard. Oops. There's a little plug into one part and plugging into someone else. These are all the London lines, Paris lines. So that's going to be a hard job to get all those little plugs in the right place at the right time. Packet switching. This, I guess, is a more modern idea where we have everyone's connected together, or there's common places for network messages to go, but we have some way of including an address with our packets so that the packet goes the right direction through the network. So your packet is going to contain a payload, your data, what you want to send, and an address. So this is a lot like mail, right? Rather than old telephone lines, because all of your mail goes to the post office, and then the post office people sort it out for you. They send it to the right place based on the address on the front of the envelope. So these days, most network protocols are packet switched. You'll have some address built in, and you'll have a payload. Not everything, not every connection protocol is packet switched. We'll see some circuit switched examples on Thursday, I think. So this allows different parts of your network to share the same physical connections. You can have one router which handles all of the network connections in your house, and then at your ISP there'll be a big router that sends network messages to everyone. And then at various parts of the internet infrastructure you can have progressively bigger and bigger routers that can handle traffic in different ways. Okay, ReactNet v2, we're going to send a message in packets. We're going to do it this way. I need two examples. I've got two volunteers. I'm going to go backwards and say that the first volunteer is Addy, and volunteer 2 is Kai. So these two folks are going to be the receivers. Now, if you send a message that is prefixed with a monocle face, that's going to mean it's a message for Addy. And if you've got a message with love heart eyes, that's a message for Kai. So someone who's not Addy or Kai is going to send a message for those things. And now we're going to go with our face protocol. It's going to be a 0 with a smile and a 1 with a laugh. 0, 1, 0, 1, 0. And you're only allowed to send 8 bits. So the packet must be in this form. 1 block address. And which Addy? Oh, there are 2. We'll have another one. I'm going to make up another emoji for the other Addy. And then we're going to have 8 blocks for your message. That's your message. Well, the two, it's going to be a message to the Addies, both Addies, or one Kai. Are there 2 Kais? No. So, okay, someone who's not an Addy and is not Kai are going to send a message to either Addies or the Kai. I'm waiting. Where's a message? Someone's got to send one. I'll do one. Getting your teacher to do it for you. All right. And we're going to have a... Got to get your tongue at the right angle for this one. And my laughing face. Oh, really good. There's a few good messages going out. So someone sent a message to Addies, which is with the old React version 1 protocol, which involved saxophones. I've got one heading out to Kai. 00000, or is it? Yeah, 00001111. Florence has sent one out to Kai as well. 0011011. That's only a 7-bit message, so I'm expecting another bit from Florence. We've got just full ones from Josh to Kai, which is exciting. So now our message protocol has gotten to be a bit more sophisticated, hasn't it? We can now send packets that go to either one person or another, and I suppose for every person commenting we could have a different react, because there are a lot of reacts in in Teams. We could be really addressing almost everyone in the class with a different React, I think. Once you start getting into those flags and the letters and symbols and stuff, there's a lot of stuff. Okay, directions of information flow, another network concept. Simplex. These always end in an X, I don't know why, but simplex means information only going one way, from sender to receiver. Much like right now, you are listening to me, and most of you are not talking to me. Half duplex means it can go both ways, but not at the same time. So I guess I could be talking to you, or we could turn the camera around, you could talk to me, but not at the same time. Full duplex means information can go both ways simultaneously. Now, mostly this kind of stuff relies on our hardware setting, because we've got to have, for simplex, we could have an out data out port and a data in port over here. We could also have some way of taking turns so that this becomes data out when it's their turn, and this one becomes data in when it's their turn, and the data will then go the other way on the same line. Or that would work for half duplex. For full duplex, we could have two lines, so that the data in is down here, data out's there. So whenever data is being sent on this line, it can also be sent on this line simultaneously. So if our hardware supports that many connections, which it often does, then we can have duplex flow both ways simultaneously. Network topology, I sort of presaged this a little bit at the start, but that's the way that different nodes on a network can be connected to each other. This can be both a physical connection and a logical connection, or I guess the way that you can address things within a network. Lots of different ways of doing this. Many of these ways are, you don't see them that often because we tend to have this kind of star arrangement a lot of the time. If you've got a router, and this could be that's your Wi-Fi router, not a TV, and you've got a laptop and you've got a desktop, that's your desktop. It's got these lights on the keyboard. And you've got your TV, which is just a huge square. And you've got your phone, which is a small square. And I don't know, what else have you got? A fridge, network fridge, and you've got your smartwatch. They're all connected to your Wi-Fi router. So it's a star topology on your home Wi-Fi network. But there are different ways of having topologies. You could have devices connected in a ring. So they've got each connected to a wire, and they're sort of sending a message onto the next person. So if we need to have a message getting to this person around here, it's got to go through all of these other nodes first. And maybe the ring only goes one way, so the messages can only go that way around the ring. There could be other ways of doing it. A bus is a cool way. If you want to be able to get messages to a lot of client nodes really quickly, you can just have one connection that they all share. So they've all got this connection, they're all tapped into it. And if you send a message to any one particular person on the bus, everyone can see it, but then you'd have to have a addressing packet, to make sure that this node receives it. Everyone else is saying, that's not my message. All right, ReactNet version 3. I thought that was what we did here. We previously did that. I've forgotten what I was supposed to do with ReactNet version 3. Circuit switched versus packet switched. I had a whole, when I made these slides, I had a whole thing we were going to do, but I've forgotten what it was, so. Okay. Here's the thing. I'm just going to pick people in the audience. Our Spike is going to be the modem, or the router. Okay. And you're going to send a message to Spike by using the celebration emoji first. Then you're going to direct it either to, I think that's Addie's, or Kai, or Florence. The Addies are still together as one unit. So we're going to have two, like a router address, router, person, and then our packet, our data. And we'll only have a 3-bit message this time for data. So someone sent me a ReactNet version 3 message. This is where the analogy is starting to wear thin at this stage of the day. I'll make one up. So we're going to send it to, and then after that, Spike the router has to send the message on to the person on Spike's network. So where's the party face? Party face, and then I'm sending it to the Addies, and then it's going to be smile, laugh, smile. Okay, so I've sent a message to Spike. I hope Spike's listening. That's the problem with with asynchronous lectures or synchronous lectures where I'm not sure what's going on the other end. And then Spike should be sending that on to Addie's in a minute. We'll see if Spike remembers to do it. Spike's turned into a router. Ah, there we go. Good work. Spike's decoded it and sent it out to the next person in line. Oh, again, things are getting confusing now. There's a mustachio guy. Okay. That's enough fun with ReactNet version 3. Thanks for playing. Serial data. Serial is going to involve data sent 1 bit at a time on one connection between nodes. Here's node A and node B. Node B, node A. Serial versus parallel. This is about the way that a connection is made between two nodes. And in parallel, you're going to have multiple bits simultaneously. So serial, you've got to have one connection, one data connection. You'll also need, just as an extra secret for you folks, you're going to need to have some kind of ground connection between the two nodes as well. Because otherwise, node B is not going to know what voltage is on that line unless you have the ground connection as well, because you've got to compare the data to something. These two are going to need to have a ground connection as well, but we just haven't got that in there. So you could be sending, a whole, I think this is a byte at once, or it's 7 bits anyway. 1, 1, 1. It's a sort of weird serial parallel connection with 7 bits. You could be sending them all at once. Serial is simple stuff. It's just one line, one sequence of voltages, and parallel gets to be more complicated with multiple wires. I'm no electrical engineer, but let's think about data connections that you know about. What about USB? What does that stand for? Universal Serial Bus. Okay, that's a serial bus. What about the connection between your microbit and the computer? Well, that's over USB, and it's emulating another serial protocol called UART. So that's also serial. So far, I haven't found any parallel connections. I believe that things like HDMI, serial, Ethernet, serial. I'm finding it hard to actually find a parallel connection which is relevant and exists. If anyone can think of one, let me know. Back in the olden days, when I was a kid, you used to have these really massive plugs for connecting printers, and they were a parallel port. That was well known as a parallel connection. It's good for printers, but so far I can't think of anything else. CPU threads are in parallel. That's not the right kind of parallel. These are only about the way that data is sent, not parallel computing. So it's whether we have multiple wires connecting to computers, sending multiple bits simultaneously, or a single wire sending bits in sequence. Most of the time, serial, even though it seems like parallel ought to be faster, right? But it turns out that simple is better. You can just make the clocking faster, send those bits faster and faster, and get very high-speed connections that way. The 3 colored cables used before HDMI. No, yeah, good point. They are sort of parallel in terms of color, but they're analog signals. So they were if you want to plug your old Nintendo into a TV, you used to have these actually they were usually, do you mean just the 5 ones or the 3 ones? Because the 3 ones, there was one yellow, that was video, and then white and red were audio. That was your left channel and right channel. And then yellow is called a composite connection, which would have color and brightness encoded into one signal in a very clever way. But there was a 5 chord one, which would have red, green, blue. That was called component. PCI slot, there's a good one. Inside your computer, where the distances are small, parallel does work. Yeah, so your CPU connected to another device can be in parallel because you've only got a short distance. I think parallel connections over long distances, it's difficult to keep everything in sync. So PCIe slot, definitely. There's a lot of little wires in a big ribbon. The ribbon's about that wide for a GPU card connection. I wonder if we'll just do some in PCIe connector. It's that kind of stuff. A lot of little wires there. What is it? I want Wikipedia. Very good point. Ooh, a number of simultaneous lanes. Yeah, well, I don't know how this works. Yep, you're right. Internal buses often are parallel. Memory will be parallel. I actually think that for PCI Express, for a GPU inside your computer, it's actually a number of serial buses in parallel, and they sort of work independently. I'm not really sure how that works. Someone can do some research and explain it in the chat. But again, we're also mainly talking about between computers or between different devices, not between parts of the same device. Someone's pointed out some connections between parts of a computer, like there's flat cables between your keyboard and the rest of your computer inside a laptop. That could be a parallel connection. Very true. Okay, now we're going to double down on serial and talk about a specific kind of serial connection and what they look like. So the first point to make is the different ways that a serial connection can be timed out. So you might have noticed that we tend to get, when we were looking at our little diagrams of bits moving across a line, we needed to know what time was. Like this, we should know to look for a change then, but there's no change. So we need to have some way of timing out our when we measure the voltage on the wire, either regularly or be looking at some other signal to indicate when we should be doing that. So if we just look at maybe we've got a stopwatch and we're looking at the wire every 1 second. Every time it says a whole second on the stopwatch, we look at the voltage. That, in the world of serial, would be called an asynchronous connection. You've got a connection here between two devices, a transmitter and a receiver, T for transmit, R for receive. And as soon as the message starts, we start our stopwatch and start counting. So the message has to start with what's called a start bit, because we always need it to start with a downwards transition. So the downwards transition is going to trigger our starting part, and then we'll have our 8 bits, high for 1 and low for 0, 1, 1, 0, 0, 1, 0, 1, 0, and then the stop bit will be bringing it high again. And of course we could go to the next byte by transitioning low, and that's our start again. Start the next byte. Start the stopwatch again at that point. So that's asynchronous serial. In synchronous serial, you could have a clock, line, and data. And the advantage here is that you don't need the start and stop bit, because the sender, and that's the receiver there, the sender can be controlling when the receiver should be looking. So you could have an agreement between them that the receiver will only look to see the data on the line, on the data line, when there's an upward transition on the clock line. So the upward transition here, the receiver looks and sees there's a 1. Upward transition, receiver looks and sees there's a 1. Upward transition, receiver looks and sees there's 0, etc. So in this way, the sender can be taking responsibility, sender responsible for timing, and in many cases, the receiver doesn't mind even if the clock line is a bit unpredictable. The receiver doesn't mind. It's only looking for the upwards transitions. So even if there's some issues with the timing, they can be solved just by the receiver watching that clock line carefully. Over here, both are responsible for their timing, so they have to agree on the timing beforehand. So receiver and transmitter responsible for timing. Cool. Timing and synchronization. Synchronous versus async. With the synchronous version, that's it, you have to have this extra clock line. You're going to have an extra wire, but the upside is that it's very easy to implement this. And that's very widely used in very simple devices. For example, SD cards can use or do use a synchronous serial method of getting the data in and out of them. With asynchronous, the transmitter and the receiver both need to have a clock timer, and they have to agree on their speed. But you only need one wire and ground. This is handy with microbits because you've only got a couple of connections that are possible. So if you want to connect to another microbit, you've only got 3 GPIO that you can clip to with alligator clips, and then there's a ground connection there. So you can actually do, if you have an asynchronous sender and receiver, you can do that with your microbit, and you can also practice by connecting to yourself. So you could have a sender on bit 0 and a receiver on port 2, ring 2. And you'll practice that in your lab this next week. Okay, where was I in my stuff? Demo time, the most ambitious and wonderful demo in all of COMP2300. Whew, this is where things are going to get crazy. We're going to do some asynchronous data sending, folks. Time for the demo. I'm going to put my scribbly board away so I've got more typing space, because this is going to be a heavy time. All right, we're going to send some serial data and we're going to look at it on an oscilloscope. And we're going to decide on a rate of bits per second. We're going to send our start bit, set the GPIO low. We're going to send the 8 bits of a byte, changing the GPIO up and down, and then we're going to send a stop bit, sending the GPIO high, and then hopefully we will do something useful with it. So I'm just going to check that this is working. Oops. Get my code out. I got my thing. Camera 1, camera 2. You've got the many Charleses on screen right now. I'm going to turn that off in a second. I've got my oscilloscope here, my little baby oscilloscope, which is just useful for demos because it's small and sits on a desk. And you can see that this little yellow line is at the bottom of the screen, which tells you that the GPIO that it's connected to is low. Now the GPIO it's connected to, what's that? I'll close my screen. It's connected with this thing, that's connected to the oscilloscope. That's connecting to ring 0. I've got this little docking thing here, which is just a convenient way of holding my microbit, but it's exactly the same as clipping a wire onto ring 0, like that. There's no difference there. So what am I going to do in my code? I've got a little bit of code already organized for myself, just because I just wanted to get a good start. I've got my output direction setting for GPIO. You know how to do that. Set ring 0 to output. And then I've got two functions here. One is to turn on ring 0 or set it to high, and the other is to turn off ring 0, set it to low. So let's just get started by preparing for my serial message. I'm going to go BL, set up output, then BL, turn on ring 0. I'll just get a couple of nops in here. Okay, let's see if this works. Build and debug. Okay, keep an eye on that oscilloscope screen. I'll run over to set up output. It went inside the function for some reason, I'm not sure why. And then turn on ring 0. And just as I did that, you would have seen the yellow line has now jumped up to the top of the screen. That's really cool, isn't it? So I know that now my sending bit is ready to go. So how am I going to do this? It's a complicated demo. I have to remember how to do it. Luckily I've got it in another screen if I completely mess it up. I think I am going to have a function that I'm going to call regularly. And this function is going to send one bit at a time. So it might be, we'll call it the send bit function. I want to have it, so sending one bit at a time. So let's make a function down here. And, whoops. I'm actually going to communicate with this function with global variables, which is a bit dodgy, but you know, if you're thinking from a high-level programming, but low-level programming, it's okay. So my first variable is going to be my byte to send. Oh, set up byte send, it must be in another file. Byte to send, and I'm just going to make it 0 to start with. And my send bit is just going to send one bit in that file. So I'm going to say bit to send. Dot word, like so. Okay. And we could, you know, get set up something in our byte to send memory location and send it in. Store, I'm just going to store a byte. I'll move it something to R1, move R1, OX, you know, I'll just send OX00, that's a byte, into byte to send. Store B, R1, R0. So far I haven't done any actual work yet, right? So what the send bit function is going to do is set up the bit, or figure out the bit we're up to. Turn GPIO on or off, depending on what it is. So on, it should be high, or off should be low, or off for 0. Okay. So how does it know what bit to send? We're going to get those important values in here. Letter 0, byte to send. Letter 1, 0. Letter 2, bit to send. Letter 3, 2. So now I've got my byte and I've got the bit that I'm up to. So the first thing I might do is do some shifts so that my or I have a 1 in a column of the byte that is the one I want to send. So I might say LSR 1 R2. Does that work? 1 in. I've forgotten. I'll have to look at my list in a minute. We'll see if it runs. It might not work. That's dumb. That's not going to work. Mov R4 1 LSR R4 R4 R2. So it's going to not LDR LSR. Logical shift right. It should be logical shift left, not logical shift right. It's going to shift a 1 up to the bit to send. Okay. Now what we're going to do is test, use the test command, the test instruction, to see if the bit to send bit is set within our byte to send. So I'm going to set test R4 R2, and if it isn't set, the answer will be 0, and if it is set, the answer will be 1. So if it is set, we want to turn the GPIO on, and if it isn't set, we want to turn the GPIO off. Okay. So I've tested it. I'm going to say BEQ, that means it is 0. Go to bit turn off, otherwise bit turn on. Bit turn off, and I've already got my turn on ring 0, turn off ring 0. So if I want to turn it off, I can go turn off ring 0. And I want to turn it on, I can say turn on ring 0. And then I have to have a return area, bit return. I just putting the bit here so that I differentiate labels from different functions somehow. And that one's got to go be bit return. Now, I've used a few registers that I need to save. I need to save R4 and I need to save LR. I've used R4 and I've used LR when I did my BL. So I'm going to have to make sure I push and pop those. But before I return, I better increment the send bit, the bit to send. So just to be super ultra careful, I need to have an equal sign in there, equal sign in there. Do I got any other things that need to be equaled? That one. People are obviously chatting to me in the chat telling me these things are wrong. What was the point of using R3? R3 is supposed to be there, so good point. and that's supposed to be R1. Okay, R1 is the byte to send, and R3 is the bit to index to send. Okay, should make sure I've got this right. R4 is now the test pattern. Test R4 with the byte. If it's 0, turn it off. If it's not, turn it on. Then we return, and in our return, we're just going to increment bit to send. And add R3, 1, and then store it back. Well, I hope that works. We could test this bit by bit, but I don't want to. I just want to write the rest of the function. So I'm going to make another function which is going to send a whole byte. So my send byte function is going to do this. I guess I could just run send bit 8 times. BL send bit 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 0, 1, 0, 1, 0, 1, 0. 1, 0, 1, 0, 1, 1, 0, 0. Okay, let's see if my program works. Set up my output, and then turn on ring 0. Okay. I'll store a byte into that memory location. And now I'm going to try sending a bit, which should be a 0. And now you can see it's low. I'll try and send another bit. Still low. High, high, low, high, low, high. So now I just need to get my stopwatch out and, right, sit here and just go click, 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 click at exactly the right time. There's got to be a better way, and there is, which is that we're going to use a timer. So I'm going to I'll take some timing code from over here, and we'll just examine that to make sure we've got it right. Put our timing code at the start. So this is just stuff from your lab last week. You enable systick, and we've enabled the systick interrupt. And we're going to store a reload value. And just make it a nice round number of 2048, which I've just picked randomly for no reason, I'm sure. We'll see if that's a true statement or not at the end. Set up GPIO. So now what's great is that I can make a function systick handler. What's it called? Systick. It's in my other file. Systick with a capital T. I always forget that. Handler. Okay, and I'm going to make that .global so that it makes sure that this is the systick handler we use. Okay, so every time my systick fires, it's going to see if it needs to send a bit. Try sending a bit. But I actually don't want it to send a bit if the bit to send is outside of our regular number. And in fact, I've missed something, because at the moment I've got the 8 bits of data, but I wanted to have the start bit, which is 0, and the stop bit, which is 1. Because we just looked on that slide previously that the serial protocol typically uses a downward transition to say, I've started my transmission now. So I need to set up that start bit and stop bit, which I'll do in a minute. But the first thing I want to do is to make sure that my systick handler only sends 10 bits of data, which is the 8 bits of actual data, plus a start bit, plus a stop bit. So I'll get it to retrieve that bit to send. R3 is the bit index to send. Okay, got to again push LR because I'm using LR. Pop LR as I'm using another function call. Okay, we'll compare R3 to 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's actually got to be greater than 9 or greater than or equal to 10. B is that BGTE? Is that really good? Oh, BGE, sorry, whoops. BGE, we return systick return if it's less than that, if less than, then send a bit. All right. So now we don't have to do our work of sending that bit by ourselves. We can just put it in place, and then the systick handler should handle it. So as soon as suppose we set up our bit to send as well, liter R2 bit to send, and mov R3 0, store R3 R2. This should send our message without us having to do anything. And we can probably watch that. I'm just going to make a little NOP loop down at the bottom to catch me. Okay, I've got my systick handler. Yeah, let's see if it works. BL send bit. I don't know why I've got a interrupt there. My signal goes high, and then I send the byte to send the bit to send, and I don't really see anything, and nothing happens, and I'm not sure why. I'm actually going to put this all in my loop. Well, I might load it up as well. Compare, B, compare to 10. And if that one is less than 10, we don't change it. And if it is less than 10, if it is 10, we change it to 0. Wait a minute, that's not going to work. The first time I want to change it to 0. Later times, I don't. Oh, my computer's going really funny now. I might set up the GPIO first, because I'm going to have to do something on my oscilloscope. I told you this was going to be a tricky demo. That's why I set a whole hour to do it. Yeah, set up my GPIO. Turn on ring 0. That's turned on. Okay. And right now I'm just going to change my trigger so that if something happens, if I get a downward bit, my oscilloscope's going to notice and just record that data for me. So I might just press play to get to there. Still nothing. I don't know, it hasn't noticed it. I'll keep stopping, that's why. Oh, there's my byte coming out. So it did show up there, but I don't have my start or stop bit set up. So I might actually make myself another helper function, which is going to be send a byte. So this one's going to have an argument. Argument will be R0, which is the byte to send. And I'm actually going to initialize my bit to send at 10. You'll see why in a minute. So, where are we? My send byte function, oh yes. So I've got to pack in, add my, my start bit and my stop bit. So if you remember, my stop bit has got to be 1. So I'm just going to make a load into R1, OX. This is going to be the 9th bit, OB, not OX. 1, and then followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. That's my stop bit. Okay, and then I'm going to OR R0, R1. And then I'm going to do logical shift left R0 by 1 step, because you know the start bit is 0. Okay, 1 and the start bit is 0. So now I've set up my 10 bits. So this should work better. And I've got to do exactly the same thing, which is to set up that byte to send. Letter R2. We're not going to store a byte, we're going to store the whole 10 bits. So we'll store R0 in R2, stored my byte to send there, and then I'm going to set my bit to send to be 0, so that we're ready to go. Now, the very last thing I want to do here is I want to wait until my bit to send is 10 before I do that. So I'm actually going to block here until bit to send is 10, because this indicates we're ready to send a new byte. So I'll load up my bit to send R2, R3, R2. And then I'm going to do a compare, R3, 10, and BEQ, or BNE. We'll go back to the top block byte. If it's not equal to 10, don't go anywhere. So you'll notice I set up my initial value of bit to send to be not OX10, actual 10, regular decimal 10. And the initial word there is 0. Okay, so what does my send byte function do? It waits until it finds a 10 in that global variable, bit to send. Then it takes the value in R0 and sets that up with a start bit and a stop bit and stores it in this location, byte to send. Then it stores a 0 in bit to send, and it doesn't actually do any of the bit sending. We wait for the timer to do that. So the timer is in control of this, this bit sending of bits so that it happens regularly, and the byte send byte function is in control of setting up the memory locations and waiting until we're ready to send the next byte. So now, instead of doing any of this, I don't have to do any of that. I can just say BL, set, whoops, get my byte to send, move it into R0 actually, and I can say BL send byte. I don't have to do any more bit sending at that point. If you got a question so far, I'm sure someone's got a question for me. So someone who's got a question, please just pop in the chat. Yeah, I would. Someone said that, wow, that's really cool. I would say, now this is pretty cool. Yeah, you ain't seen nothing yet, folks. Stick around. This is going to get more. The last 10 minutes are the critical ones. Okay, let's see if this actually works, because, like, I don't know. I spent a whole day yesterday having a very small problem with serial sending. What? Where's my... It's not working. It hasn't compiled. What did I do? I've got the wrong offsets in 56. Ah, whoops. Letter equals. That's going to be a problem, isn't it? Okay, we got that to work. All right, I'll skip down to the bit where it actually does some sending. I'm now running. You can see nothing's changed on the screen, but it's got a little sign here. It's too small to see, but it says waiting. It's waiting for a downward trigger. And run my send byte code, and then just go. Oh, there's my byte. It worked. I got my byte. And we can see, if we look really closely, the byte was 10101100, which should be, that's two downs. I'll make it a bit bigger. Oh, I can't make it bigger because it's already happened. It's 2 down, 2 up, down, up, down, up, because we're reading it little endian. Start with a, I'll use this as a pointer. Start with a downwards transition, that's our stop bit. Then we got our 2 O's, then we got 2 1s, O, 1, O, 1, and a stop bit. Now that is pretty cool, folks. We are sending bytes on the wire. And it only took me 40 minutes, or even 35. Pretty good, if I do say so myself. Now, just for kicks, I'm just going to move this into my NOP loop, because I'd like it to be there. So I can do this without worrying, because I know that my program is not going to be able to send more bits until the previous bits have been sent, because my timer is running, getting those bits onto the wire, and it's not going to try to overwrite that byte until we get until we get to the whole of that byte being sent out, including the start and stop bit, all of those 10 little signals. Okay, now I'm going to run it again in this version, and I'm going to turn the thing off because I just want to be able to reset my. See, now we've got heaps. They're just going and going and going. as soon as that it runs out of bits to send, it goes again through that send byte location. I might put in a delay here, just using the standard old MOV 0, 10. Maybe I should have a letter. Letter 0 equals 10, 1, 2, 3, 1, 2, 3. BL delay. So I've just got a little bit of a delay, 5 million cycles, just to clear out my screen so that I can catch one at a time. Oh, come on, what's going on there? Why would it not let me do it? Is it because something's wrong? No. There we go. So now we've got our single byte being sent. You can see that this one's a bit different. It's 10101010, so it starts low, high, low, high, low, high, low, high. And you can see there's an extra long low at the start because half of it is the start bit, which is ground or low. All right. Folks, someone said their mind is blown. Well, thank you. As a teacher, that's the highest compliment you can pay me. I have to say, folks, this is within your power to do. You have learned how to use timers. You have learned very well how to use GPIO. Every student in COMP2300 right now has the capacity to do this. You don't all have oscilloscopes to see it, so you'll have to make do without that. But I guess that's one of the harder things, is it's easy to do this when you can see it on the screen. If you're ready for your mind to be blown any further, may I introduce you to this thing? This is a synthesizer. I'm just going to get reposition my camera a little bit. Have a look at OBS, sorry about that, for a minute. My camera over here. And you might notice that over here on my microbit, I've got a little wires connected to the microbit. It's essentially connecting this brown wire to a serial output port on this plug, which connects to this little plug, and that little plug is going to connect right into this synthesizer. This is a format called Midi, and let's just go back to our slides, because I've got a slide to show you about how this works. Someone said make a teletype. This is much more interesting. A teletype? I'm not going to make a teletype. I'm going to make a synthesizer, man. We're going to look at some. I've got these things in the slide, so you can check out what this looks like zoomed in. I made these last year, or 2 years ago actually. So things are a little bit different, but pretty much the same idea. Midi. So this is a serial connection between things that control music, like keyboards, and things that create music, like synthesizers. So here I've got a synthesizer, and I'm going to turn my microbit into a music controller, sending some instructions from a music controller. When you press the key down, it sends the instruction, it goes to the synthesizer. And the way that this works, MIDI, medium, and frames. MIDI this is from the 80s, I think. 1980, MIDI 1.0 came out. It's very early serial connections. It's sent over basic serial connection, UART, which stands for Universal Asynchronous Receiver Transmitter. Just an asynchronous serial connection. The little wire can only support one direction. If you need two directions, you have to use two wires. And this is the crucial bit, 31250 bits per second. So how many bits per second are we going to have to do? We've got 64 million cycles per second on a microbit, because it's a 64 million 64 megahertz CPU. And if I divide 64 million by 31250, I get 2048. I'll put it on this little screen. 2048. So You can see my reason for choosing 2048 as a good amount of time. That translates to 32 microseconds, which is small, right? 32 microseconds. You couldn't sit there and tap it out, in other words. Each frame has one start bit, 8 data bits, and one stop bit. This is all very convenient because this is exactly what we've just made, a system that can send a byte with one start bit, 8 data bits, and one stop bit. So, the thing with Midi is that you have 3 bytes in one message. If you kit down one key on the synthesizer, make this one work. Whoops, I'll turn off the something. That's a bit boring, isn't it? This one's nice, music box. 3 bytes. One is a status byte, telling it what kind of message. The camera's covering the slides. Yeah, it's not too bad. I'll move it to change to RH small for a minute. We're going to go back to the camera in a minute. Status byte. This one means note on. That means I've hit a note on the synthesizer, pressed it down. The next byte is going to be the note. There's 7 bits for note, so MIDI supports 127 different notes. I happen to know that note 60 is middle C, which is that one. And then we've got a volume or velocity byte. So it's velocity because that's kind of how hard you're supposed to be hitting the key on the piano. And sometimes that would be measured by the speed of the key snapping up, so they call it velocity, but also hardness or loudness or pressure. Similar ideas. So we're going to send not just 1 byte, but 3 bytes. Not just 1 byte, but 3 bytes. And that's just what we're going to do right now. So it's not really going to be very much harder than what we've done already. We've got all of the information ready to do it. Just get my camera back so you can see what's going on. We've got everything ready to do that. And if I can remember how my code works again. Oh yeah, here we go. So I'll go into my loop. I've got my delay there. I'll just make it a bit longer because I'm going to have to set up 3 bytes to send. 1, 2, 3. The first one is going to be my status byte, OX90. That means note on in channel 0. There are 16 channels in Midi, because it's the low half of the status byte is the number of the channel. And this only listens on channel 0, so don't let me mess that up. I'll move in R0 again, another byte for 60. That's going to be the middle C. And this one, I'm just going to use maximum volume. Maximum volume. Oh, I remember the hex for that one. It looks cooler if you use hex, doesn't it? OX7F, that's 127. And I'm going to send all those things. So I'm just going to put not inside my loop. I'll just compile my code and let's see if this is going to work. It does it. Let's have a look on the scope. So there's my message, my MIDI message going by, and it's actually 3 bytes all together really quickly. Because as soon as we finish 1 byte, the time it finishes 1 byte, my little byte sending program notices and sends the next. So the first was 9, 0. What's that going to be? OB 1. Whoops. What's 9 in hex? I've forgotten. That's 8. 1001. 0000. Then the next one's middle C, which is a 60. I've forgotten what 60 is in hex. I'll look on my slide. 3C. That's OB3, which is going to be 0011. 0011, and the C, that's 10, right? So it's going to be 1010. And then 7F is OB01111111. So we can start to decode this message looking at the scope. There's our start bit. Then we've got 4 O's, then 1, 2 zeros, and then another 1, and a stop bit. Next note, start bit and stop bit. Oh, I got that wrong, 3C. I thought C was... I've forgotten the pattern, bit pattern for 3C. What's the... Someone tell me the bit pattern for 3C? C is 12, ah. Yeah, so there's 3 O's, then 4 1s, then another 1. And then we've got our 7F, which is just going to be sort of 1 0 there. That's our stop bit for the next byte. 1 0 there, start bit 1 0, and then 1s until the end of the frame. And that's our 3 MIDI frames. Now I told you we're going to make some music, so let's do something more interesting than just one single note. I'm going to make a register I haven't used yet, R5. It's going to be 48, which is a bit lower, 12 notes lower than MIDI C, middle C, and we're going to increase it each time we go through our loop. And so every time I run my frame, I'm going to add 1 to R5 until we get to, oh, not a 1, I want to add 2 so we get a cool scale. It'll be a whole tone scale. Until we get to like, what's 48 plus 16? 64. Comp R5, 64, be greater than put the delay at the start. It's a loop, so it doesn't really matter where I put the delay in. It'll get delayed somewhere. Be less than loop. BLE loop. Less than or equal to loop. And else we are going to just move a 48 back into R5. So we'll be doing some MIDI sequencing with a very simple kind of baseline pattern. I want it a bit faster. Let's go twice as fast, so I'll cut that delay in half. And a little bit faster than that. It doesn't seem quite, it's not quite jazzy enough. It's a bit more like what I want. People are asking questions or something. Yeah, that's a bit more better. So now, because I've got a synthesizer, I'll just get some maybe a bass sound, get one of those. Oh, that's a bit better. Anyway, making some music with a micro bit and a synth. That's the end of my lecture, folks. If you got a question, I'm a bit shocked at myself that I managed to pull that off. I have done a similar demo like this before, but I didn't try to write the code in the lecture. Yeah, boss battle music, something like that. Pretty distorted there. Thanks for the cool messages, folks. Look, I mean, I have a synthesizer, so I've got something I can use, but you have a microbit. I haven't done anything in the code here that you can't do. This is 100% doable by COMP2300 students who are up to this point in the course. So I know that these things are cognitively hard. I mean, it did take me a while to work out this example, but not that long. And I knew what I wanted, so, but if we go back to just our existing first principles, we need to have a start bit, a stop bit, and 8 data bits at a certain rate. That's not that complicated. You can do that with GPIO controlling. And you can use a timer to time them out. It's handy that I've got my, you can see the note changing, by the way, which is pretty cool. I wonder if I can change to an auto trigger here. Nah, it's not going to work. Normal? Oh yeah, there we go. So it gives me every note. Yeah, you'd have to write an FM synthesizer for the microbit if you want that sound through the speakers, which is a bit wild. I'm going to take a photo of this. It's just so cool. Get some sounds. And a photo for my slide. Someone's got a good question. Is the only purpose of the stop bit to reset to high after a byte is sent? Exactly. That's exactly the purpose of the stop bit. So I'll just move this to part of the screen where it's easy to see. If we don't have that at high, well, I guess it's nice to have this kind of 2-bit reset. Now, I'm not a hardware designer, but the way that these things work are set up by some of the limitations of how hardware has to be designed. And we're talking about limitations that existed in 1960, which is when this serial protocol was set down as being a standard. So it might have been in that time like your hardware would have to require a little bit of time to reset the receiving of another byte, which now we have the capacity to do things much faster. But we're talking about 60 years ago, what technology was available, which was not an actual computer doing this, but a mechanical system, like physically a typewriter that would be decoding these bytes. It would have to work mechanically. You have to kind of just follow the instructions with these things. It's part of the protocol. There are actually other aspects of this which I haven't done. There can be another bit in there which is called the parity bit, which just is a little bit of error correction. Now it lets you know if the bit has been received correctly. If the parity bit is like the oddness or the evenness of the byte which has just been received, of the addition of all of its numbers. So that can give you some indication about whether your message was correct or not, but we don't need it for Midi, so I'm not going to deal with it. Another thing is that no no programmer in their, generally, no programmer in their right mind would usually use this method to send serial. They'd be using the hardware built into the microbit, which is specifically designed to send serial. If I go to the NRF, now where's my resources? There's a bit of hardware called the UART, which is specifically hardware designed to send bytes over a serial connection. So you don't need to run your own timer to send a UART connection. You can just use the UART peripheral, which has a timer. I'll show you how to set that up on Thursday, I think. So this is in some way, this is the hard way, but it's the way that lets us learn how to do it using a timer. Someone said, is it possible to code a real score like a piano's? That will be really challenging. Well, I mean, the microbit, a piano score is just a sequence of MIDI messages sent at a certain time. So yeah, it's possible to time it out. If you've got all of the data in there, you could time it out and have it be sent. I guess it would be a little bit tricky to get 2 notes at the same time because this synthesizer only supports 3 notes at the same time maximum. So it's not easy to make it. You can't have a whole piano score with this, but you can have a melody, have the starts and stops. I just chose to have this kind of techno thing because it's nice just to have a continuous sequence of notes. Get some more things. Yeah, that's a bit cooler. So, yeah. All right, 16:03. Folks, I'm exhausted. I've got to go. I'm going to turn my volume down. I'm going to call that a day. And on Thursday, we'll return and look at a few things about the consequences of this, the consequences of what we've just done, why it was hard, what we can do in software to make it easier. And maybe we'll look at the right way of doing it using the UART peripheral. You're very welcome to today. I hope to see more folks on Thursday, but I know it's a more difficult time to attend. So if I don't see you, make sure you catch up with the video afterwards. Folks, make sure you go to your lab this week. Make sure you're prepared with an assignment pre-submission, submitted before your lab starts. And have a great week. I'll see you on Thursday. Oh, it didn't work. I normally have my big wave finish. See you later, folks.